Hello everyone. Today I will introduce a plot boundary extractor module that my research group has developed. This is written in Python, and the main objective of this module is to delineate the plot boundary in agricultural application that is mainly used for field experiment. And this will help to do that plot boundary delineation process as seamless as possible. Hopefully this tutorial is going to be useful for many agriculture scientists. So the URL that you can get information about this module is listed up here. It's github.com gdsl/plot-boundary-extractor. And this is an open GitHub repository there where anybody can come in and actually clone it to your need. And what I'm going to do first is I'm going to first clone this repository to your local machine. So for that one, let me open up this in a window. I actually I'm logged into the machine, workstation. There is an NVIDIA GPU on it. So I'm going to move into the directory where I can play with it. And I believe I already cloned this in a plot boundary extractor on my machine. But just in case you don't have it yet, you can just copy this in a URL. Then come back here in a git clone and paste that link, and that will clone that repo to your local repo. So I'm not going to just do that because I already have cloned it. So if you move into this plot boundary extractor directory where everything is in a clone over here, there is all the other information, but the main one that we like to work on here is called this d2spy, because we're using data to science and a Python module to pull the orthomojang images from the data to science platform and extracting in a plot boundary. So this the Jupyter notebook file is going to be the one that we're going to be working on. Coming back here, if you'd like to see how it looks like, you can click this Jupyter notebook. That will open up in your browser. So I will start from the top. Extracting field experiment plot boundary using plot boundary extractor module. Like I mentioned earlier, this will be the tutorial to show you how to extract field experiment boundary, plot boundary using this module. And this is in the main written by Hansa Kim. He's a PhD student in my group and myself. And the procedure that we implemented in this module is being developed as a journal paper. The title is Developing a Segment Anything Model Based on a Framework for Automated Plot Extraction. And this paper is currently under review in Precision Agriculture Journal. So later when we actually have this paper published, then we will include the citation information here so that if you're using this module to do any plot boundary extraction, you can use proper citation later. So first we need to install this in a plot boundary extractor module into your machine. So what we're going to do here is we're going to first set up a virtual environment using Conda. So we need to run this command here. So conda create -n or -n. This is in the virtual environment name, and -c is the channel for conda, and we're going to be using conda 4 channel, and we're going to be installing GDAL and Python version 3.10. So coming back to this window, I'm going to put this on one side. I'm going to put this on another side. I'm going to do conda create name. I already have PBE virtual environment created on this machine, so I'm going to use something else. I'm going to call it PB2. And if you're doing it for the first time, you can just use whatever conda environment name that you like to use. I'm going to use conda forge. I'm going to use GDAL Python 3.10, and I'm going to say yes automatically to everything that conda is going to ask you to do. So This will take a little bit of time. Let's give a few minutes. And they are installing all the required packages. And next thing that you're gonna do is you need to activate this virtual environment that you just created. So I'm gonna do conda activate plot-boundary-extractor 2. In my case, this name of the virtual environment shows as in the front of my shell with a the bracket over there. Next thing that we need to do is we're going to install this in a plot-boundary-extractor module using pip. So pip install plot-boundary-extractor. Go like this. There's a bunch of packages that is being installed at this moment. And next thing that we're going to do is we're going to install torch. And depending on configuration of the machine that you are working on, if you don't have an NVIDIA GPU, you need to install torch version that says CPU version here, which is pip install torch torch vision. And in case you have an NVIDIA GPU installed and configured, in this case, this machine that I'm working on is equipped with NVIDIA GTX 4090. So I'm going to be installing this version. But if you don't have an NVIDIA GPU, you have to run this command at the top, which is going to install torch in the CPU version. So I'm going to copy and paste the link, and I'm doing this installation over there. Then we have to install SAM. So we're going to install this segment anything module using this command over here. So I'm going to be copying this one over here. I will wait until this torch installation is done. Then I'm installing this SAM. And the last thing that you need to do here is you need to actually download that pre-trained SAM module, SAM model, to your local machine. So you can just do this command here. I'm not going to do it because I already have a copy on my local machine, but let me just do it. So I'm going to just download it. This is about 2.5 gigs. So let me see. What did I do? Oh, I didn't copy. So I was running the same command as in earlier. First, I need to copy. Place it here. They are downloading this pre-trained model. This is about 2.5 gigs. Office has a pretty decent internet connection, so this download is not taking too long. But depending on the internet connection you have, this might take a little bit longer. Okay, so once you have this one, then now you have everything that is needed installed, and also make sure that this same printed model is downloaded to the local pathing over there. Then now you can just open up this Jupyter notebook, d2spy plot extraction demo.ipy notebook file. Open, and in my case, if this is your local machine, you can just simply do Jupyter Lab. But this machine that I'm working on is a remote machine, so what I'm going to do is that I'm going to open up the Visual Studio, and I'm going to be connecting to that machine remotely. Give me a second, I'm doing it right now. So open this up. And let me just close all the other file that is not needed. But if you come back here, plot boundary extractor, if you open up this d2spy plot extraction demo, Jupyter notebook file, this is going to be the one that is going to look like. Let me just close this file out. And this top part, this is essentially the same information as readme, the markdown file that we looked at earlier. It has information about how to install this plot boundary extractor. Next one that we're going to do is that we're going to importing all those in required module. So we're importing OS module, leaf map, date from datetime, and d2spy workspace is being imported. And this is in a D2S environment that I created personally so that I don't need to type in my ID and password to log into data to science platform. If you don't have it, you can just comment this line out, and you can just specify what is your email address, and it will ask your password, to log in. And the last line here is actually importing this in a plot extraction module from plot boundary module over there. So what I'm going to do here is I'm going to just run this code, and we are actually loading all those required module over there. Then now what we need to do here is we need to find the data product from the data to science platform so that we can do the plot boundary delineation over the data product. And the way how this data science platform is configured is they have this hierarchy that I'm showing over here, and this tutorial will be pulling the data set from PS2 instance, which stands for Plant Science 2.0 initiative at Purdue. So if you click this link, you'll find more information about it. And this PS2 instance, which is ps2.d2s.org, is open to public. And this instance is currently being managed by my research group and hosted out of Purdue Data Center. And D2S stores all the data and data product using following structure. Like I mentioned earlier, that once you log in, you'll have your own workspace, and you can have a multiple project in your workspace. And in each project, you can have a multiple flight. And each flight, you can have raw data and data product 1, 2 in whatever number of data product. So the way how you're going to find the data product that you need is you need to first get access to the workspace and choose a flight, choose a project, then choose a flight, then choose a data product. So that's going to be the process that we are going to go through. So first, getting a workspace from data to science. Like I mentioned earlier, I already configured this D2S environment in a module or in a file that contains my ID and password. So if I just do workspace, connect, and the URL of data to science instance, it will connect automatically. But if you don't have this environment set up, then what you have to do here is you need to add your email right after this URL. Then it will ask you to type in your password, then you should be able to log in. In my case, it's going to be simple. Just run the code, then I'm going to be logging in and getting access to the workspace. Okay, this one is taking a little bit longer than used to, but that's fine. Depending on the internet connection, this may go very quickly. I think the first time that you're getting connected to might be taking a little bit longer, but and a lot of times I can actually get my workspace much quicker than 10 seconds that I'm showing over here. Next step is getting an API key, because we are going to be accessing data product that might not be open to public, and the way how we are authenticating yourself with data to science is, of course, one way of doing it is using ID and password, but some of the third-party module that we're going to be using, essentially, for example, this leaf map, they don't know how to authenticate with the data to science, so you need to grab the API key from this data to science platform. So the way how it works is, any workspace has an API key associated with it. You just store it. If there is no API key stored, then they will complain. If you have one, then they will set this API key as an environment variable. Then we are going to be also using the dynamic tiler. We're using t-tiler, and t-tiler endpoint, we're going to be using the one from the data to science as well. So I'm going to just run this code. It just ran in no second. Next, you're going to get all the projects. So workspace get project will give you the list of all the projects that you have an access to. But I'm also doing one additional step, filter by title. So I'm only querying a project that has a Cornell name in it. In my case, I have an access to this Cornell with program UAV data set as a part of the Wiki project, but depending on your account, the accessibility, this may not be visible, but it's going to be only give you the project that you have an access to. So let me just run this code. So getting all the project that has a name Cornell in the title, we're just printing out, and you're gonna see these 3 project is being returned. We have a 2023, 24, and a 2022 Cornell WIT project over there. Since this tutorial will be working with a 2022 Cornell WIT dataset, so I'm choosing this in a third one. Python uses a zero-base index, so this index 2 will refer to this third one over there. So I'm choosing this project. You know what? Let me just do a quick correction, because this is a collection of projects. So let me just call this as a project. So I'm gonna just grabbing a third project and assign that as a single project in a project value variable that over there. So let me just run this code again. Probably I will have to update my Jupyter notebook in a repo later. So we chose a project which is pointing to this 2022 Cornell WIT dataset. Now, what we're going to do next is we're going to find a flight within a project. So we're doing the same thing from a project. We're going to get all the flight. We have ton of flight for this specific project, but we are only showing a flight that is flown somewhere in between this start and end date. We imported in a date module from datetime earlier. So basically what this one is telling us is that I like to have the data set collected between April 1st and May 31st of 2022. So that's exactly what we are doing over here. And printing this out. If I run this code, then you can see that we have a 1, 2, total of 7 flight over there. Okay, so this should be 7 flight. Sorry about that, because I was not paying attention to zero-base index. And what we're going to be using is we're going to be choosing May 11th, the one that we're looking at here. May 11th, this is RGB dataset. So this is going to be the one that we're going to use. So the index is 1 over here. So out of all the flight, we're going to use May 11th RGB flight. Next, what we're going to do here is pretty much the same the process as earlier. In the flight, we can have a multiple data products. So we are getting all the lists, print them out. And you're going to see there are 4 different data products. First one is an orthomosaic images. Second one is an excess greenness index layer. Third one is a digital surface model. Fourth one is a canopy height model that's unloaded. But for this plot boundary delineation, we need to use this also. So we are choosing first data product as a data product that we're going to use. Okay, next one, what we're going to do here is, once we get this data product, we'd like to visualize this using a lib map. So once I run this in a code here, then now you're going to see we are using USGS native images and a base map layer. Then we are adding cloud optimized GeoTIFF layer. This is a URL of this cloud optimized GeoTIFF from Data to Science. Like I mentioned earlier, since this is not open to public, we need to provide this an API key so that you can actually access this data set through this lib map. So this, as you can see, we have these orthomosaic images displayed over here. This is the we trial that we're working on. So once we have this one, what we can do here is that now we can use plot boundary plot extraction in a function inside that plot boundary extractor module. But this module takes multiple parameters as an input. I'm going to go through this in a list here, base layer, essentially what is going to be the base map that you like to use to run your plot boundary extractor module on. In this case, this is going to be May 11th, the orthomosaic images, which is stored in this way over here. You also need to provide an API key so that this module can access that restricted data. And this clip file name, the way how it works is that in order for this module to be able to process data, we are creating a local copy. So what we are doing here is that we are actually clipping the area that we're going to specify in the next step and making a local copy and save this as a 2022 Cornell Wheat example. And clip boundary, this is the actual boundary to do the the clipping. And the way how it works is it is using leaf map, draw control on the last draw over here. So basically what you need to do is, scroll up here, go to the map, and using this polygon tool, I'm gonna be click around this, the experiment plot, then close it. Then I'm just generating this in a polygon over here. So whatever the polygon that you do the last time will be passed into this clip boundary information there. And how many rows that you got and how many columns you have. This is 22 by 13. So if you come down here, what I'm doing here is that this is the row direction. So we have a 1, 2, counting all the way. This is going to be 22. We just in a column, we 1, 2, all the way up to 13. So that's the number that I got from this drawing over there. And what is the width and height of the plot? And there are many different ways of doing it. Essentially, what you need to do here is you need to zoom in and using any tool that you have, measure the width and height of this plot. In a lot of cases, you might have already that information handy when you design your plot. And if you don't have it, although another way of doing it is that you can load this exact same orthomosaic into QGIS, and you can use a measuring tool to measure what is an approximate dimension of this plot. Each plot is going to be. In a lot of cases, this information is already available, and this happened to be 3.7 meter and 1.0 meter high. It's a 3.7 meter wide. And the unit, we don't have it over here, but this unit is coming from whatever the unit that is associated with this orthomosaic that you're looking at. In this case, this orthomosaic is generated in a UTM zone. I don't know what is the zone number over there, but all the UTM uses a meter as a unit. So that's where you're coming in here. 3.7 is going to be meter because this orthomosaic uses a meter as a unit. Okay. And the point per side is 10. I just intentionally setting this value low. Basically, what it means here is that in order for this SEM to work, they need to have some seed point distributed around this region so that they can use those seed point as a kind of detecting an object over there. What 10 is telling you that we display distributed 10 seed here, 10 seed over here, so it's going to be overall 100 seed is distributed within this polygon so that we can do this object detection. And if you want to have this all plot detected in a single shot, you can increase this number to higher, something like 64. And I'm know by my experience that if you do this, all the plot will be detected automatically. But the reason why I'm setting this too low is because I like to have some of the plot to be not detected so that I can go over how you can add those in a missing plot manually later. And IO threshold value is basically what is going to be threshold value that you're going to use to say whether this is in a plot or not. This is coverage threshold value. This is also we are using calculate canopy cover from this RGB. Canopy cover value from this RGB imagery, and we're using this threshold value to determine whether this is going to plot or not. And lastly, we have an alpha file name in GeoJSON. They're storing this in a value in this one here, and you also need to specify what is the pre-trained model. In this case, I'm going to be using my current directory and SAM-PTH because we already download this in a file to our local directory over here. And next, we just do the plot extraction, save it as in a plot, automatic detection, and I show the result. So if I just run this code, they just loaded these images. I mean, they are not clipping it because I just ran this code before. But if this is first time you're doing it, what it does is they use that polygon. You just pull this orthomosaic images from the data to science platform, make a local copy, then load this in the clipped images into your instance. I mean this Jupyter notebook running this code. They just get the initial plot number is 69. They say that there might be missing plot, a lot of them. So they think that they're doing some refinement process going through it. And you will soon see the outcome. So give a few seconds. And I think increasing this number to higher value may actually run quicker, because whatever this detected and missing plot is 217 means that there are about 217 plot based on the row and column number that you specify that is not detected in an initial kind of attempt. So they're trying to locate those missing plot one by one. So this is taking a lot longer because we use this point per site to be low value 10. So probably what I can do is once we get this result, see we're going to increase this number to see what kind of result that we get. So processes are completed. They're doing some additional processing, and this is the result that we get. So all those plot, it may look like not a rectangle, but I think this is because of the light and launch value, the precision is not good enough at the zoomed out version. But if you zoom in, you can actually see that all those plot has been placed beautifully out there. But the one that I was talking about here is that you see there is one missing plot over here. And this is going to be the one that is not detected, and that there is a procedure where you can actually manually add them or delete them. For example, let me just zoom in here. Let's say this is the plot that you don't want to be added. Basically, what you can do here is once you do mouse hover over here, then you're going to see that the ID of that plot is 70. So what you can do here is that you can delete that the ID 70 from the plot that you got. So if I just run this code, what they're doing is that they are manually deleting that the plot that I just we looked at. They'll be the plotting this new plot they detected. Shows up soon. Give me a second. So let me just scroll down. You're gonna see that this ID 70 has been removed from this detected plot list. But what about if there is anything that is missing? So basically what you can do is that you can add an additional plot, but it also uses that draw control last row over here. So what you can do is, let's say I'm like to add this one back because this one's not detected automatically. So once you can zoom in, you can use this polygon here. Don't draw too big. Try to draw a smaller box within the plot. Just once you do this, coming down here, using this polygon that you just drew as the attention, the SAM will be trying to delineate the plot boundary, the one that you just drew over automatically with the dimension that you specified earlier. So if I just run this code, they're only applying SAM over that mask area that we just drew. They just successfully added a missing plot. Then they're going to be updating this information, and you're going to see that plot over here, the one that you just was missing earlier has been added in automatically. You can just do the same thing again. For example, if you like to have this one back, I can just click and draw. And I'm gonna just run this code one more time. then you're gonna see soon that, hey, they just did, and I added a missing plot over here. And coming back down, now you have, all the plot has been delineated, successfully. Last step here is you can actually store to your, GeoJSON file, whatever the format that you have. The previous GeoJSON file that you created, if you go up, we specify this is an alpha file name. This one is a GeoJSON file, but this one is using whatever the coordinate that OrthoMosaic uses. In this case, UTM. Specification of GeoJSON, everything should be in WGSN 84. In this case, UPSC code for that one is on a 4326. So whenever you are save this plot boundary to a file, this one will be using WGSN 84, which is an EPH code on a 4326 as a file. So please make sure you save this as a 4326, because this is going to be something that GeoJSON file to expect. So if you just run this code, now you have this one saved in your computer, then you should be able to load this one to your whatever the GIS software that you got. So if I like to do this, let's say I'm going to pull this information. Let me go back to this one. Let me open up another terminal here. I'm going to go to desktop. I'm going to be copying this file here, white. And the file name that I used was in a plot boundary GeoJSON. So I'm gonna copy, coming back here. I'm gonna copy this file to local machine here. Let me just pull up this data science and a plugin. I'm gonna be logged to d2spy. And let me pull up my password really quick. So copy and paste, login, then I can get all the list of projects that I have access to. The one that we worked on is 2022 Cornell. So where is it? This one here, right? And the May 11th. And let me see which is the one. So I believe this is a multispectral one. This is the one with the CHM, is the one that we worked on. So add this in a layer. This is the one that we looked at. And now let me just drag and drop the file that we downloaded. Desktop here. Oh, give me a second. So I'm just drag and drop this in a plot boundary. We just download it. Let me turn this into a transparent one. Then you can see everything is placed in perfect location. This is pretty darn good. So I hope this before we just finish it, I think I just made a case earlier. We might be able to do this a lot quicker by increasing this number of seed points to a higher value. So let's do 32. I think 32 is going to be enough. So let's rerun this code with that configuration and see if you can get the result quicker. Because I believe this will give us a lot less number of missing plot, and this might give us result much quicker, but without annually adding any missing plot. So let's give a few seconds to remember what was the time it took for the previous try. See, yeah, the initial plot is 217. I think earlier was like an 89 or something. So they only need to detect 72 more. So this is going to be I believe going quicker. Let's give a few more minutes. I'm also looking all the way to this side because I have 3 monitors over here. we got the result out. Let me just scroll down over here. Oh, we're still missing this one here. Okay, interesting. That one is detected. We got the pretty much the same result. So let's see if we can increase it to 64 to see if we're getting the result that we want in a single shot. But I think one thing that we could observe, earlier was that the time it took to run previous code was shorter than the first try, because there's a much small number of missing plot from the earlier try. So we are doing side of 64. I mean, the other one that I was talking about is I have 3 monitors. My camera is here, but all my recording is happening on my left monitor. So I was looking all the way, this way. I think my neck is starting to hurt. My center monitor here is vertical monitor, so it is not the best one to do actually in a screen recording. So you see, now we only have 4 missing. So hopefully this will give us result that we got. You see, everything has been detected without any missing plot. So, in this case, you don't have to do manual operation over here. All you need to do is sort this. And if you scroll down, there is a step-by-step example to show you, we just plot extraction, visualize the layer, rotation if needed, generate the initial plot, and etc. Probably can just look into it. So anyway, I hope this was the helpful tutorial, and we will come back with additional tutorial. The one that I'm trying to develop in the future is once we have this plot boundary extracted, then how we're gonna add all those field layout information. We've been working with T3 team from Cornell, and also in a rebase from Cornell, so that we can pull those field layout information from rebase in a database, and merge those information back to this detected plot boundary automatically. That will streamline your the downstream process a lot easier. So thank you very much, and I will see you next time.